Hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Now, in this discussion, we're going to look at an interesting part of the concept of mechanics, and this is going to follow our previous discussion, whereby we had looked in an exclusive way the concept of potential energy, kinetic energy, and work. Now, in this discussion, we're going to look at the kinetic energy for a varying force. And in our previous discussion, I had mentioned the concept of kinetic energy for a constant force, which we had given especially using Newton's second law, which assisted us in trying to define or give a formula for, of course, showing that a specific aspect of the kinetic energy. Now, in this discussion, this is going to be a similar form which we are going to look at. But in this case, we're going to look at the concept of varying forces. Now, suppose we have a net force that is acting on a particle in a particular direction. So we can represent this specific aspect of a force using this particular initial. And if the force acts on an object, so I can give this one in just a summary form statement, which is going to assist us. Now, suppose we have a net force that is going to act on a particular object in a particular direction, which we are going to give in x direction. So this can be illustrated using this specific example from the previous discussion which we had for Newton's second law of motion. So we are going to consider this force F acting on an object in x direction given as such. And therefore, we are going to give this specific force as the summation of F in x direction given as such. And therefore, we are going to consider from Newton's second law of motion, which we had said, and therefore have this summation of this specific force, the x given in terms of mass times acceleration in this x direction given as such. So we can just leave this one without introducing the brackets. So we're going to have the force in x direction equivalent to mass times acceleration in that specific direction. Now, suppose we consider the distance of motion or the displacement from this initial, for the object from initial position xi to x final. Then we can represent this specific aspect of motion of the particle in terms of the work done in moving this particle from the initial to the final position, by giving it as an element or the total work done in trying to move this object. Now, this one can be given in form of an integral of the form given from x initial to x final, and this is going to be given in terms of the summation of fx, of course, dx given as such, which is going to be the integral of the summation of this element of from x initial to x final given as such. So I could prefer that we are going to do it using this specific summation sign, which is basically going to be an integral form given as such. So therefore, this is going to be considering this specific representation for the summation of the force or the total force given in terms of mass times, of course, acceleration in the x direction. And therefore, we can give this version of the summation of work given in terms of the integral from x initial to x final. And this is going to represent this aspect of a mass which we have given. So basically, this one we can consider this one given in terms. So we're going to consider this element of mass which has been given in terms of ma x dx given as such. So whereby this is going to represent the total force which was involved in that one from the Newton's second law of motion, which have said. So this basically can be evaluated, whereby we're going to see that from equations of motion, we see that acceleration can be given as a differentiation of velocity, or the first differential of velocity is going to give us acceleration. So we're going to have this one as mv dv over dx. Dx are given as such. So this is going to be a differential of velocity, which is going to give us an element of course, what we call acceleration. So still this is going to be given in terms of x initial to x final, given as mv dv given as such. And our further evaluation, we are going to consider this particular aspect of mass, which is going to be constant. and therefore we're going to take it out of this specific sign. So therefore we are going to have this given in terms of the integral mass, the integral of x initial, x final, v dv. So we're going to differentiate this one v with respect to this one, and of course v dv, and then this is going to assist us in trying to find the representation of work done in trying to move this particular object. So this element of w is going to give us a product of v squared. So in this case, we're going to have this one raised to power 2 all over 2 plus c. So this is going to be a normal integral as we normally perform integration in our basic integration or basic integrals from mathematics concept. So in this case, it is going to give us a final part of this specific equation, whereby if we do a substitution for x initial and final, this is going to give us a version of the equation that we can give in terms of summation of w is equivalent to half m into v final minus v initial. And this, of course, is going to be in terms of the squares of these particular values, as we have seen from this specific integration, of course, which we have done in our previous example. So this is going to be basically giving us a formula for finding a kinetic energy for varying forces. And we can consider various evaluations in terms of examples, which I'm going to give a link in our description boxes. So kindly check our description boxes for various links, and also ring that notification bell and subscribe to be getting other updates we do in this specific product topic of mechanics. So that is it for now, guys. By God bless you. Catch us in our next video.